are in listen-only mode.
Hello and welcome to our latest webinar in the iFormulate Introduces series on crystallization science and agrochemical formulation. We'd like to say today thank you to our sponsors who are Technobis Crystallization Systems. Speaking today will be myself, Jim Bullock, and I'll be talking about the basic principles of solubility and crystallization. Then I'll be handing over to my colleague David Calvert, who will be picking up some of the practical importance of these themes in agrochemical formulation. This webinar will last about 45 minutes and it is being recorded, and it will be made available to you as participants afterwards. If you'd like to ask any questions, please use the GoToWebinar chat functions or question functions, and we'll try to answer those questions at the end. We will be muting you as the audience to prevent background noise intruding on the webinar today. We'll start with a little bit about iFormulate. We're a fairly young company founded by two experienced industry professionals. We've just celebrated our third birthday, in fact. We bring our own experiences and knowledge gained across many industries in different functional roles, and combined that knowledge with the expertise of our associate partners who we bring to help us out on specific projects, all in order to assist our clients with their needs. We divide our activities into three business areas. In iFormulate Consult, which is the relevant area for today's webinar, we carry out innovation and technology consulting, mainly in formulation technology, for client companies in private sector industry. As iFormulate Strategic, we've carried out and assisted strategic projects in the area of formulation for sector bodies and associations such as the UK's Knowledge Transfer Network, the National Formulation Centre here in the UK, and the Royal Society of Chemistry. And under iFormulate Skills, we design, deliver and promote training courses and programs in formulation science and technology, and these may appear under our own banner or they may be in partnership with third parties. So our sponsors today, as I've said, are Technobis Crystallization Systems, company based in the Netherlands and active in a number of markets relevant to crystallization, including pharmaceuticals, agrochemicals and fine chemicals. Technobis manufacture laboratory systems which enable you to measure, characterize and control some of the properties that we'll be talking about in a bit more detail today. So things like solubility curves, the metastable zone, the formation of polymorphs, and the control of crystal habit. All of those measurable and characterizable with this kind of equipment. So here's the overview for today's webinar. I'll be starting with some basic principles looking at solubility and what factors can influence solubility, how solubility can be predicted or measured, supersaturation and crystallization, the thermodynamics and kinetics of that, moving on to some interesting phenomena and important phenomena, Ostwald ripening and polymorphism, taking a look at mixed systems before finishing on some watch outs for the real world. And at that point then I'll hand over to David, who'll be overviewing agrochemical formulation and then picking some agrochemical formulation types where these phenomena are particularly important and interesting, particularly focusing on such things as stability troubleshooting and diagnosing the sort of problems that you might get, and mentioning also the potential use of additives. We'll finish off, as we said before, with a short question and wrap-up section. So let's start off talking about solubility. Before we think about crystallization, we need to understand solubility. We always think of solubility as a rather simple thing, but what is it really? When we come to measure it experimentally, it can seem a little bit trickier. So the easy bit, the solubility is the amount of solute that will dissolve in a solution to form in a given volume of solvent to form a solution. Now that solute can be usually a solid, and we'll assume for today's purposes that the solutes are solid and the solvents are usually a liquid, and that's what we'll assume for today's purposes. But the tricky things come when you start thinking about equilibrium conditions, measuring the solubility. How do you actually measure that quantity? What about supersaturation? What is that? What about the effect of impurities and strange solid state effects? What about predicting it? What about the effects of conditions such as temperature? So we'll start off by just taking one way of looking at solubility. I like to look at solubility as an equilibrium, but with the solute essentially distributed between the pure solid state and the solution state. And the position of that equilibrium is determined by thermodynamics, by the free energy of the system, and in essence by the interactions between those components. So very simply, if you have a system where you want to increase the solubility, what you want to do is make the solution state more favorable. In other words, you want to increase interactions between solute molecules and solvent molecules, and that's on the top little diagram there. One other thing you could do is to make the solid state less favorable, and you might do that by thinking about the interactions between solutes molecules in the solid state, and you might even think about the interactions between solvent-solvent molecules. So it's about molecular or ionic or atomic interactions and the balance of those forces that determines where your solubility will lie. Let's look at what factors practically can influence solubility, and that's something you might want to influence yourself. So very obviously, the choice of solvent, as we said, that affects the molecular interactions between the solute and the solvent. And we'll look at it briefly in a minute at the use of solubility parameters and the similarity principle to see how you might choose a solvent for a system. You might also think about the nature of the solid state of the solute, thinking about things like the crystal packing interactions, thinking about a particular crystal or amorphous form of that solute and what properties that might have. The particle size of the solute plays a role too. Smaller particles mean higher free energy, and higher free energy means higher solubility. So that's an important solid state effect. One's very simple property that you can look at as an indicator of crystal packing energy, for instance, might be the melting point of a system. And as you take your thoughts further, you might come across and think about the sort of complex solid forms that can be produced. So co-crystals and hydrates, for instance. Then there are impurities and additives. Impurities, you don't intend to be there. Additives, you do intend to be there. So impurities usually have the effect of reducing the melting point and increasing solubility. And indeed, you may add additives to your system quite deliberately in order to solubilize a component of your system. But of course, you need to think about specific effects. For instance, if you have an ionic salt as a compound which is your solute, then the addition of metal ions might in fact cause precipitation and reduce solubility. So it's something you might need to think about. And the fourth factor we've listed here is really the condition, the experimental condition that you're in, especially temperature. And that's one thing that we will be considering today. So let's move on to prediction of solubility. How can solubility be predicted? And various attempts have been made to predict solubility in systems on the basis of molecular structure. And probably the most successful way of doing that, and most widely used way of doing that, is to use solubility parameters, Hansen solubility parameters being the most common. This is a scientific way of expressing the common principle like dissolves like. So really what you're doing here is describing the solute and the solvent with parameters which relate to the forces going on in that molecule, so dispersion forces, polar forces, and hydrogen bonding interactions. And that's very useful for selecting solvents for your solute, and indeed for producing mixtures of solvents, which might be very effective. It's not an absolute method, however. It doesn't predict an absolute solubility, and it can't take into account crystal packing effects. Molecular modeling methods, on the other hand, in principle can account for all interactions. Essentially what you're doing is carrying out free energy calculations here. However, these systems are complex, they require a lot of expertise, and they require a lot of computer-intensive calculations. So they're not for everyone. And they're usually done in special circumstances and not routinely. We've actually produced a little overview on our website. You can have a quick look at that when you finish the webinar for an introduction to some very simple equations on solubility that you might find useful. So that's prediction. How about measurement in an experimental sense? Well, the important thing to remember that in measurement of solubility, the saturated solution has to be in contact with an undissolved solute at equilibrium. So that raises a number of questions. For instance, equilibrium. Have you got there? What time does it take to reach equilibrium, and how do you know when you've got there? What about temperature? Are you controlling that properly? So often you'll need multiple data points. You might need temperature, concentration, different solvent amounts added. And how do you measure that concentration in the solution? Can you do that gravimetrically? Can you use a chemical analysis technique such as HPLC? You might actually need quite a lot of complex equipment and analytics to carry that out and to do multiple heating and cooling cycles. And you also may need to rely on manual intervention and judgment. So very often one of the simpler ways of working out whether you've got solute present is just to use your eyes. But how reliable and reproducible is that? So in principle it's easy, but in practice it can be tricky. And one way in which this process can be made easier and quicker is to automate. An example here, we've just taken the Technobis Crystal 16, and that's a piece of equipment that is automated, can be used for small volumes. It has programmable temperature ranges, it can be used with multiple solvents and concentrations, and that important detection of the solid takes place through integrated turbidity measurement within the system. So that, in a way, reduces the complexity by automation and makes it rather easier to measure solubility. Second potential complicating factor then is the phenomenon of supersaturation and the metastable zone. Not everything that you see is determined by thermodynamics, and in fact supersaturation is an example of that. In a supersaturated system, the solute concentration is actually higher than the equilibrium solubility. So in other words, a supersaturated solution is thermodynamically unstable. However, the kinetics essentially overrule the thermodynamics, and the kinetics prevent crystallization happening if the concentration of your system remains within the metastable zone. And if you want to carry out a controlled crystallization, that can take place within the metastable zone. So for instance, if you're growing large crystals, you can do that with seeding, with controlled cooling or controlled evaporation or controlled addition of an anti-solvent. So quite important to understand where your metastable zone is and how that relates to the solubility curve. So the dotted blue line here is the supersaturation curve, and the red line is the solubility curve. And in this example, you're starting from point A where you're unsaturated, so you have solute in solution, you're not saturated, you cool. You don't actually form any crystals, so you go into the metastable zone as you move towards B. Once you hit the edge of the metastable zone, then crystals will be formed, and if you're careful about your crystallization, you can then cool in a controlled manner and slowly down to point C through the metastable zone, growing your crystals at a time until you reach point C, where your system's in equilibrium and thermodynamically stable. So that's a bit about supersaturation, a bit about the metastable zone. So what's happening during the process of crystallization? And crystallization is usually broken down into two steps to make it easier, and that's nucleation and growth. In nucleation, solute molecules or atoms or ions move around with the solution according to Brownian motion, colliding with each other all the time, attaching and detaching each other, detaching from each other at random. Within the metastable zone itself, if the nucleus is going to grow spontaneously, it has to reach a critical size. Now, it won't do that unless you do something to the system. And one way of making that nucleus become critical is to add seed crystals. And if you add seed crystals when you're in the metastable zone, then crystallization will happen. However, once you're beyond the supersaturation limit and you're in the labile zone, that's the upper left-hand part of the diagram that I showed on the previous slide, the nuclei will actually form spontaneously. Because the solute concentration is so high, there are lots and lots of collisions between molecules, solute molecules, and therefore very high probability of forming nuclei of the critical size. So they will form spontaneously in the labile zone. Then we think about the next step, which is crystal growth. In the metastable zone, crystals will grow once critical nuclei are present, and they grow by, let's assume that we're talking about molecules of solute here, by molecules attaching to the various faces of the crystal. And we'll come on to what that means for crystal shape in a little bit. In primary nucleation, just because these are two terms actually which are used quite commonly, primary nucleation occurs in systems which don't already contain crystals of the solute. So for instance, homogeneous spontaneous nucleation, which is usually a precipitation event occurring in the labile zone. It's homogeneous primary nucleation. Heterogeneous primary nucleation is nucleation induced by foreign particles. And secondary nucleation, which is usually the case when you're doing a controlled crystallization, then you're inducing that nucleation by the presence of parent seed crystals in the metastable zone. So there's just some terminology that you might see. A very brief sort of recap of the thermodynamics and kinetics, but doing this without mathematics. If you like the mathematics, there is plenty of textbooks that will tell you about that. But I think for the purposes of this webinar, it's probably a lot better if we don't do that. In the undersaturated region, then, just to recap, the solution state is the thermodynamically stable state. Any crystals added will dissolve, and critical nuclei cannot form in that undersaturated region. In the metastable zone, the solution state is thermodynamically unstable, but the kinetic barrier prevents spontaneous formation of any nuclei of critical size, so there won't be any growth. Growth is thermodynamically favored, so if there are seed crystals added in the metastable zone, then they will grow. So growth is favored, but nucleation is not. In the labile zone, supersaturation is very high. There's no kinetic barrier to nucleation, as we've just seen, and nuclei form spontaneously. It's a very high nucleation rate, so what you get is the formation of many small crystals in the labile zone. So it's now worth thinking about, when you're doing a crystallization, an intended or an unintended crystallization, why do crystals appear to be in different shapes, and how can you influence the shapes that might be formed? Well, the shape of a crystal depends on the internal crystal structure itself of that material, and also on the rate of growth of its geometrical faces. And some faces will grow faster than others due to attachment energy considerations and the kinetics of growth of those faces. And the slower growing faces, as we'll see in that little simple 2D diagram there, the slower growing faces are the ones that you're going to see more of when you look at the crystal under a microscope. So in this example, the slower growing face is at the top and the faster growing face is on the side. In this example, it grows into a needle because the side face is growing faster than the top face. So it's longer than it is tall in this case. That's something that can be influenced. So the growth rates, the relative growth rates of the faces, and therefore the crystal habit, can be modified by the solvent again, by the degree of supersaturation, by the impurities that are chosen, and by deliberate use of additives. So quite a lot of work goes into producing additives that can modify crystal shape by blocking growing faces, for instance. So that's crystal habit. What about one of my favorite topics, which is Ostwald ripening? And this is a phenomenon that real formulators see quite frequently and have to deal with quite frequently. It can happen in all sorts of systems. I think most people will have come across these in dispersed or suspension systems or dispersion systems where you have a solid dispersed in a liquid or indeed a liquid dispersed in a liquid at times. What happens in Ostwald ripening? You have a size distribution within your system. The larger particles will grow, the smaller particles will dissolve. And that is a thermodynamically driven phenomenon. So essentially large particles, as we've seen before, are more energetically stable than the smaller ones. And that's because smaller particles have fewer surface, have more surface molecules which are energetically less stable than the ones packed into the interior. So smaller particles, less stable, they'll dissolve, and bigger particles will grow. So it's thermodynamics, so it's going to happen eventually if you have a polydispersed system, but you can slow it down. You can get kinetics on your side. So you can slow down ripening by starting with a more dispersed particle size distribution in the first place. So if you've got a more regular particle size distribution, then that process is not driven as quickly, and you may, as we've seen before, we may be able to use additives which can block particular phases and slow down the rate of Ostwald ripening from happening. Another phenomenon which formulators will see quite frequently is that of crystal polymorphism, and indeed the appearance of amorphous solid forms. Polymorphism is a pretty simple thing to explain, so and those are pretty simple diagrams there on the right hand side. So what we're showing here is that the same substance, which is the blue cross in those diagrams, may appear in more than one crystal form. So it may stack up in a number of different ways, and those crystal forms are known as polymorphs, depending on how those ions, atoms or molecules are arranged in the solid state. Importantly, crystal polymorphs which may be of the same substance actually have different thermodynamic stability, so they have a different packing energy, so their solubility and other physical properties will differ from each other. So it's important to know what you've got and what the properties of that polymorph might be. And indeed many solids also frequently have an amorphous form, which is in general less thermodynamically stable than any of the crystalline forms, and that's worth watching out for as well. And actually when you're looking for crystal polymorphism, it's worth bearing in mind the words of Walter Macrone. Walter Macrone is known as the father of modern microscopy. He actually did a lot of work of analysis on the Turin shroud, and there he is. And his famous statement, as far as I'm concerned, is that essentially if you want to find polymorphic forms, every compound actually has them. The number of forms that compound has is just proportional to the amount of time and money that you're prepared to spend on researching that compound. So if you spend enough time, you'll find plenty of polymorphic forms. And they can be distinguished by techniques which many people will be familiar with, for instance, X-ray powder diffraction, by differential scanning calorimetry, by infrared Raman spectroscopy. And the screening for polymorphs of a new substance, as we've seen earlier on an earlier slide, can be automated. So that's something that might be considered as well. Now, another phenomenon worth looking at when you've got complex systems is the potential for formation, deliberate or accidental, of mixed systems within crystalline solids. So I've got 4 examples here of mixed systems. On the top left, we have a solid solution. The solid solution is quite easy to think about. That normally happens, for instance, in molecular solids where solute B has a very similar molecular structure to solute A. It might differ by, say, 1 carbon atom, and it replaces molecules of A at random in the crystal structure of A. And the physical properties will vary gently as B replaces A within that system. In a stoichiometric co-crystal, we have essentially a new ordered crystal structure, and that happens when molecules of B and A have specific interactions between each other that makes them stack up in a particular new way. In a solvate or a hydrate, then you get crystallization of the solvate or the water, which is often the solvent, within the solvate to form a new ordered crystal structure. And in eutectic mixture, you don't have co-crystals at all. You have separate crystalline domains of the 2 substances, A and B, which are intimately mixed in the solid state. And again, you get different physical properties from that eutectic mixture as well. So let's move on, before we hand over to David to take up the formulation baton, to things that you might want to watch out for in the real world. Supersaturation, well, a supersaturated solution, if you're formulating a solution, supersaturated one is unstable to crystallization. So once you've got impurities there, you might have crystallization occurring. A stable solution might seem all right at room temperature, but it may become supersaturated when it's cooled. Ostwald ripening, well, we've mentioned what can happen with suspensions. Suspensions may become unstable because essentially particles will grow and you have an increased tendency to settle out. And that process, if you want to find out whether it's likely to happen or not, can be accelerated by the process of temperature cycling. So as temperatures go up and down, you may actually see Ostwald ripening occurring. Crystal polymorphism is important because the less stable polymorphs for you in an application might be in pharmaceuticals or agrochemicals, might be an attractive thing to have a less stable polymorph. They'll be more soluble and therefore more bioavailable. However, they'll be less stable in the solid state. So suspensions of a less stable polymorph may actually recrystallize out as a stable form, causing a problem with the stability of your formulation. Crystal habit, well, that's important very often during the filtration step when you're actually making an organic solid, synthesizing and isolating an organic solid. For instance, if you've got a press cake, then the crystal habit can strongly influence the filtration and filtration rate for that press cake. So that depends a lot on the crystallization conditions, what crystal habit you'll get. If you're making a solid product with dried solid crystalline powder material, then powder flow properties can depend quite strongly on crystal habit as well. And in mixed systems, just remembering, as we said before, they may have very different properties from their single components. They may be unstable with respect to their single components as well. So what could you, bearing in mind those potential problems, what could you or should you know about your system? This is all about minimizing risk in product or process development. Characterization costs time or money, but it does reduce the risk downstream. The choice is yours, essentially. But here are some things that you could do. If you're making a solution, you might want to know about solubility curves. How does the solubility vary with temperature? What about supersolubility? What is the influence of impurities and additives? What about any mixed solid phases? How can you characterize those? What might be the properties and composition of those? Is your system likely to undergo Ostwald ripening? What might be the influence of additives or impurities on that ripening behavior? What crystal polymorphs could you get? Which one's more stable? How might you characterize or fingerprint those? When might polymorphic transitions occur? At what particular temperature, for instance, might they occur in your system? And finally, what have you got in your system that might influence crystal habit? Might you want to put an additive in there to change the crystal habit? So with that, we're going to move now on to David to take over and think about the industry context and where some of these phenomena that we talked about just now might be important. So David, over to you.
Okay, well, thanks, Jim. And I'm sure we all saw there's lots of lovely theory there, but it's all a matter of, well, does it really matter, and where exactly is this important? So if we think about what Jim spoke about, he spoke about solubility and crystallinity, and they seem to be important where there are two phases, and there are solid and liquid, or solid and liquid, or gas and solid, as he went through. And if you think about that in formulations, well, I guess in essence almost every formulation is a two-phase system. So some of the things he spoke about are certainly worth bearing in mind as we move forward. And today we said we would focus on agrochemical formulation. So let's just have a brief overview of what exactly is in an agrochemical formulation. If we look at an agrochemical formulation, we'll see that it's composed, as with many, of an active ingredient which is there to do something. So that's the herbicide, perhaps, or an insecticide, or a fungicide. And then we have formulants, or additives, as you may call them. And what they're put in there to do something, obviously. They're in there either to improve or maybe to maintain the stability. They're in there maybe to disperse the active, or some of the performance is there to be improved by the actual additive. So they're in there to do something. So you've got a mixture, and you've got that type of mixed system that Jim was talking about. So in agrochemical formulations, there are specific formulation types, and those go by two letter codes. So we've chosen 4 where we thought the solubility and crystallinity are particularly important. There are soluble liquids, and that has the code SL, and lo and behold, well, yes, that would be where solubility you would think would be important. We then have suspension concentrates, which Jim's spoken about some suspensions, going under the code of SC. We have emulsifiable concentrates, perhaps the most traditional and the most widely used formulation with the code of EC in agrochemicals. And then we have what we might call the new kids on the block, the oil dispersions, which go from the code of OD. And we're going to take a little bit of a closer look at each of those in turn. So let's start with soluble liquids with the code of SL. And I guess if you really want to start off, Jim, we're going to move on. If we really wanted to start off and say, well, what are we going to have as our simplest formulation, then if it's soluble, we'll go for a soluble liquid. If you take a look at the latest pesticide manuals, there are 127. I checked last week, they're actually listed as being soluble liquids. And in amongst those is the most successful herbicide called glyphosate, is an SL formulation. Glyphosate, if those of you don't know, was launched by Monsanto in 1974. And it has sales upwards of around about $5 billion, according to a survey done in 2014. So I think most of us would like that to have that in our portfolio, or like to have invented that. But glyphosate is not just a simple formulation or a simple product. It's marketed as a number of different salts. There's the ammonium, there's diammonium, dimethyl ammonium, isopropyl ammonium, potassium and sequisodium. And if we start to look at the solubility, again, I went and looked at the pesticides online version, the pesticides manual, and you start to see glyphosate there, and they give you some solubilities. Glyphosate itself in water is not particularly soluble, so 10.5 grams per litre. And again, taking note of what Jim says, all about the equilibrium conditions, so that's at pH 1.9 and 20 degrees C. If we go down a number of these, we'll see the ammonium salt with a different pH and a different solubility, and then the isopropyl ammonium, perhaps the most common one being used, with a good solubility, potassium and sequisodium. So the equilibrium conditions are very important, and also it's important to think that glyphosate itself is the active. The salt, if you started to look at a solubility based on weight, all the different salts obviously have different weights. So quite often when you're talking about glyphosate, I found some figures, they talk about the acid equivalent. So in this case we see that the isopropylamine at 20 degrees C and pH 4.6, you can get 47% of the isopropylamine acid equivalent into solution. The sodium slightly lower, potassium at 44%, ammonium and trimethyl sulfonium TMS. Again, you can see slightly different pHs, but at least we have a little bit more of a comparison there, and the isopropylamine is probably the most favoured salt being used in glyphosate. So what does that mean in terms of let's have a look at the commercial glyphosate and what actually happens in practice? Well, there are often mixtures, sometimes of different salts. Often they have an adjuvant, and those of you who've worked with this will know taloamine ethoxylate, TAE, which is under some pressure itself, and there are many options there to replace that, but it does increase the solubility and enhance the uptake by the plant. You'll find in many formulations surfactants to do the same thing, and you'll find some other pesticides. So quite often with glyphosate you have camber or 2,4-D added in there, and again, if you think back to what Jim spoke, that means you've got a mixed system in there. So what effect's that going to have? When you do get a commercial glyphosate formulation, it's 120, 240, 360 is the most common, 418, 680 grams per litre of active in the ingredient. But clearly solubility is important, and important for the most significant herbicide in the world. So let's go on and just take a brief look at some of the other formulation types that we spoke about at the beginning. The suspension concentrate, or SC as it's known, strangely enough is a solid suspended in a liquid medium, often water. You can do quite well and get it up to about 60% of the active ingredient in these formulations. And the other additives in there, well, dispersants to disperse out the solid, wetting agent, defoamer as you're dealing with water. You'll have a stable or a rheology modifier, or what can be called a good old-fashioned thickener to actually thicken it up. Antimicrobials, antifreeze buffers and some other adjuvants. And if you look at the pesticide manual, you'll see that there are 322 pesticides in the latest pesticide manual. So a very popular format in agrochemical formulations, but not quite, I guess, as popular as the Emulsifiable Concentrate, or EC as it's known. This is a solution of the active ingredient with emulsifying agents in a water-insoluble organic solvent, and then when you add it to water you get an emulsion formed. In these you typically see up to 40% of the active ingredient. They have solvents, co-solvents, so again looking at solvent mixtures to improve the solubility, emulsifiers, antifoams, and other adjuvants, and names are interesting: stickers to make it stick to the leaf, spreaders to make it spread out on the leaf. And there are 444 pesticides listed as being as an emulsifiable concentrate. And then if we go on to the new kids on the block, the oil dispersions, or ODs as they are known. This is a non-aqueous suspension concentrate. So the active ingredient is actually suspended in an organic solvent or an oil. You do only get 20% active ingredient. You have again similar things such as emulsifiers, dispersants, rheology modifiers being particularly important in this formulation, and some stabilizers as well. But you'll see there are only 16 pesticides listed in the pesticide manual. It is a formulation type that does work well in terms of compatibility, improved uptake, but obviously there are certain issues with oil dispersions, and certain actives are not suitable to this formulation, particularly if they're performing well enough in other formats. So I'm always one to keep up with the news and try and look at how formulation is being reflected in the news. And those of you who followed the US election will see that Donald Trump recently was involved in trying to say we need to look at our immigration policy until we, I think he quaintly put it, what there is going on. Well, this is actually common for, I believe he was speaking for agrochemical formulators, also want to know what is going on in their own formulations. So Donald Trump actually speaks for us formulators. And if we look at what's going on in most formulations, we're really fighting a battle against instability. And that instability can be down to a number of things. It can be settling, it could be flocculation, it could be some of the crystal growth that Jim spoke about earlier. But they all lead to compacted ingredients with a clear layer on the top. And knowing the cause can sometimes lead to the solution, trying to get a stable formulation. But this instability is all formed, and Jim touched on it a little bit, all formed by Brownian motion. So we've got some collision events going on. So in those events we have attractive forces, which are can be van der Waals, which can lead then to coagulation and flocculation. And this is something that we're trying to avoid, and therefore we're trying to get those particles not to hit one another and be repulsed. And to do that we often put on surfactants or some stabilizers that form a double layer to make that electrostatic repulsion, or we also might look to make a steric hindrance from them combining with one another. And if we're successful, then we can end up with dispersed particles, and we have a stable colloid, and we have those particles dispersed in the medium. But sometimes if it goes wrong and we get things like Ostwald ripening happening, then we have some problems. And on this next slide we've just got a little simulation of what actually happens with Ostwald ripening. So if you follow this molecular simulation, you'll see particles there, and what you'll start to see as Ostwald ripening is happening, the smaller particles are starting to disappear, and those larger particles are growing and growing and growing and growing. And if you wait long enough, you will probably start to see just one particle, and that's what the theory says, is that there will be one particle. So what does that mean for you if you actually don't have any control or knowledge of what's going on in your system? What's the actual outcome? Well, your actual pesticide just might not work. It might not be efficacious. It might be a different polymorph that doesn't work as well. It might be that it's not available in the formulation. You might need, if you haven't got quite the solubility, to have a larger dose to get the efficacy. You might have a non-optimum concentration. Obviously, if something's happening, your shelf life is going to be changed. And at a smaller level, you may end up with particles blocking filters or blocking nozzles. So how do you stop this? Well, first of all, you've got to know what's going on, and how can you diagnose and make progress? Well, we're all doing stability tests, and as good formulators know, the best thing sometimes is the human eye. So the picture there just shows some sulfur crystals growing from a sulfur solution. If you start to see crystals growing, then immediately the alarm bells sound and you need to look for something to solve that. You may obviously, if you can't see it with the human eye, you might need to use a microscope, and we always say that that would be the first piece of equipment to buy in any formulation laboratory. If you can't see it on a microscope, some measure of particle size may well actually help you. And zeta potential may also give you indications of which zone you're in and whether you're in a stable zone. And those of you who may have listened to one of our previous webinars on DLVO will know a little bit more about zeta potential. And if you're looking for crystallinity, then DSC and X-ray diffraction are often tools that can be used. So these are the type of techniques you might want to use. If you think it's agglomeration going on, then what would you actually do to troubleshoot your agglomeration? Well, as we talked about, you may well use an optical microscope. You may use a PSD measurement, laser diffraction of some form, or zeta potential. And you might be saying, well, has the particle size increased on storage? And if so, then my particles are coalescing, so maybe I need to look at some different surfactant. Are they forming flocks or agglomerates? Well, I might just need to disperse it a little bit better. I might need to look at a larger level of that to give electrostatic or steric stabilization and make more of the particles stable. If I'm looking at crystallization and I think crystallization is my problem, then I may well start to again use an optical microscope. But at this stage I might want a hot stage there so that I can look at some of the phase diagrams Jim has talked about and see what I'm looking at. Laser diffraction PSD obviously of use, and DSC and XRD we spoke about. And also, you'll see some photos in a future slide towards the end from Technobis' Crystalline, where you can actually see this happening and take pictures of things as they occur. So you might be looking for crystals growing from the solution when it's in the metastable zone, or you may be saying that the system's moving into the labile region and crystals are growing spontaneously. Temperature, if you've got that hot stage, you may be able to look at the effect of that. And you may also see a polymorph forming, and again Jim's spoken in a little bit of detail about what it is. So what do you do? If you're a formulator, the first thing you say is, well, I can add something to there. And done a little look around in terms of just on crystallization, and there's a number of additives, crystal growth inhibitors, often protective colloids, comograph copolymers, a large number of surfactants, and there are some patent activity, and there you can see 2 patents I found, one about preventing crystallization in a spray of a fungicide, and then on a suspo emulsion composition, and that's a combination of a suspension and emulsion. So you can imagine there are all sorts of things going on in there. But if we, again, just look at what actually can be happening and what an additive can do, then we've got some pictures here using Technobis' Crystalline. And on the top one, they've added in the additive for an active ingredient with amino acid functionality. And in the bottom one, there's no additive. And what you can see from the blown up pictures, again taken from the Crystalline, is that using the additive you can actually control the type of crystals formed and obviously the crystal type that's in there. So you can add additives and you can see their effect using the Crystalline. So at that stage we're coming to the end of our 45 minutes. We're just about on time, I think. So you are going to remain muted, but I did see, I think, that we had a question, if I remember rightly.
Yes,
which came in, and I think it's one for you, Jim.
Yeah, I'll pick up. There are a couple of questions I think we've got time for here. So we've got a question: is it true that some crystals have a memory of their shape? I've been told that sugar, for example, will once crystallized and melted, placed into solution, reform into the same crystal shape. Well, yes, but it's not what you would call a magical memory or anything magical going on. Essentially, the memory of the shape is built into that internal crystal structure that the crystal forms due to those crystal packing interactions between the molecules and to the rate of growth of those faces. So that's an example of crystal habit being formed. And if conditions are always the same, then the same crystal habit will form each time. So in a way, that's a kind of a memory effect, but there's nothing magical about it. The second question we have here is on some examples for anti-solvents concerning controlled crystallization. So probably the best example of anti-solvents might be when you have, let's say, an ionic solid solute, which is soluble in water, and the anti-solvent might be something that is water miscible, but is not a solvent for for that solid. So an example might be, let's say, an alcohol, which is water miscible alcohol. As you add the alcohol to the water, then your system is progressively less stable. Your solid is less soluble in the water mixture, and it will start to crystallize out. So alcohol water mixtures is a nice example of that. I've got another question up. Are less stable polymorphs more prone to Ostwald ripening? They're certainly more prone to dissolving. They may ripen, but they may indeed convert to the more stable polymorph. That may be a more probable route. We've got a final question, I think, now that we've got time for. Is a different crystal habit a different polymorph, or are they distinctly different? No, a crystal habit, a single unique polymorph may form in a number of different crystal habits. So the internal crystal structure is which polymorph it is. The external appearance is the crystal habit. So they are different things. Crystal habit is determined by that rate of growth of the faces. So I think that's probably all we've got time for and the time available.
Yeah, if there are any follow-up questions from anyone, please send them on to info@iformulate.biz and we'll deal with them. Just to wrap up, you might also be interested, if you're into agrochemical formulations. We're delivering on behalf of ATI an introduction to agrochemical formulation strategies. The next one's on the 1st to 2nd of March in London. We are working together with the University of Leeds to do a spray drying and atomization of formulations 12th to 14th of April. It's in its 3rd year. It's going from strength to strength, so it's 3 years now, and we will be having a taster webinar which will be coming up in the near future, so keep your eyes peeled if you're interested in spray drying. And then we've just launched our in-person training, and the first 2 courses for this year. We've announced a inkjet formulation fundamentals on the 9th of June and adhesion science for formulators on the 1st of December. Go to our website under training and events and you'll get information and registration details. Feel free to contact us. It's my duty now just to say thank you all for your attention. We hope you've got some value from today's webinar, and we look forward to welcoming you to another one of iFormulate Introduces webinars. And a final thank you to Technobis for sponsoring this webinar. Thanks very much. Bye-bye.